All right, this is actually a day 2 that I just threw together this morning to help us out, hopefully, with completing the square a little bit. Because again, completing the square is used a lot in a mathematics other than what we're doing it for, and so it's good to be able to have that skill. And I think it also helps to know kind of why it works, and that's what hopefully we're going to show you today. And it actually goes all the way back to the Greeks, which is a couple thousand years ago. All right, they were solving quadratics. Okay, and as you see here, though, it says the symbolic algebra that you're accustomed to, like x squared plus 2x, they didn't have that. All right, they just had, oh, if I had this segment, I had this segment, and I wanted to know this, what would the answer be? So in fact, that didn't come up until it was actually the algebra we're used to is Hindu and Arabic is kind of where that came from. And that's maybe 1,000 years, not even quite that old. But the Greeks didn't have that, so they basically solved it by using a compass and a straight edge. They constructed the answer, which is just amazing. But the key here is at the end here is the Greeks, they hadn't considered 0 as a number yet. 0 mathematically is actually a very young discovery. Okay, and they didn't really worry about the negatives, because to the Greeks, you had 5 of something or you didn't have 5 of something. You didn't have -2 of something. Why would you tell somebody you had 0 of something? Why would they care? Right? You either have 1 or you have 2, or you have, so they were counting. You see, that's why they didn't care. And so they didn't really worry about that. And so a lot of these times for their quadratics, they never got the negative answers because they weren't concerned with them. Okay? And so as you can see here, it says that the Greeks showed that you could solve these 3 forms right here. X squared plus bx equals c. And the reason they had to write it this way is because they didn't have negatives. See, if I subtract the c over here, it's a negative c, right? And so they were like, that's nonsense. We're not going to do that. And then, so they had a construction you would do for a. If this is the setup you had, they would say, do this. Okay, they wrote it in big, long words, though. For them to write a would be a huge paragraph that would take up the rest of this. They would describe it. It didn't look like, it's way better to see x squared plus bx equals c than a big paragraph explaining that. You can only imagine how ridiculously hard it is to decipher that. And then they had one for b. Again, huge long paragraph describing it, and then here's how you solve it. All right? But again, it's much better in our notation we have now. But again, you see the bx is over there, and it's not negative. Okay? And then we have this last one, c, which apparently I copied over before the editing was done on Word. That's why you see the little underlined green there. And it would be set like that. And as you see here, the one we're going to be concerned about is a, because each one of them had its own construction. It was done differently. But we know now we have one formula that'll do them all, right? But I'm going to kind of show you where it all came from, okay? So we're just going to focus our attention on option A, the x squared plus bx equals c. The reason is I believe that this construction, we're not actually going to get the compass and straight edge. We're going to draw a sketch of what they would have done, okay? And so as you look at that one, it really doesn't seem as though that fits A, does it? Right? But can I get it to fit A, the one that we have here? Can I make it fit that pattern? Yep. Pretty easily, right? Because the pattern is x squared plus bx equals c, right? So how can I get my problem to look like that? Well, yeah, add the 39, get it out of there, right? Okay, and that sounds very similar to our completing the square notes before, right? Is that we wanted to be in control of that constant, okay? So it's very similar. So exactly, we're going to add the 39 over. And so our version is x squared plus 10x equals 39. This is the problem we are going to solve with a picture and then a little bit of algebra. Okay? Because I told you yesterday, completing the square just seems like a really weird terminology. Why would you call it that? Otherwise, you know, what in the world's going on? It's because you actually do complete a square. Okay, and you're going to see that in a second. Because this x squared, they wouldn't say x squared, they would say a square, meaning there's a square out there somewhere. And so that's how they would word it, and so that's what we're going to do. We're going to make a square. And our square is going to be x by x. Do you agree the area of the square that I just made is x squared? Right? X times x. And so I'll put that in the middle. And so basically I have drawn a picture that represents this x squared we have here. Right? I've drawn a picture for it. Now there's many ways you can draw the 10x part of the picture. Okay? But the easiest way for what we're going to do is put a rectangle off on this side and a rectangle up here. Really, it doesn't matter, just 2 adjacent sides, okay? And seeing I split the 10x basically up into 2 rectangles, correct? And so, well, it was a 10, and if I split it to 2, it's going to be 5 each, kind of, right? And so this is 5, right? This is 5. But do you see how it's really a rectangle? It's 5 by x, right? And 5 by x, each one of them. Are you with me on that? So the area of just this one over here on the right, the area of that one is 5x. Are we in agreement? And this one appears also an area of 5x. So do you see if I add all three of these pieces together, I got x squared plus 5x plus 5x. That's the same thing as x squared plus 10x, isn't it? So basically, the area of this green and blue thing put together better be 39, because that's what it says over here. You see that? We've divided it up. But now we're going to actually complete the square. Can you see a little bit bigger square than the one that I began with? But it seems like a chunk is missing. The top right is missing, isn't it? But if I complete it and I make it, now do you see how this bigger one is now also a square? So we have now, in a picture format, completed the square, and that's why they called it this, because they actually were completing squares when they did it. And the funny thing is we actually know that that's 5 by 5, so we know the area of that's 25, right? Because it's 5 by 5. Everybody see how we knew that? Because this one here is 5, right? And this one over here is 5, so then that one's got to be 5, and so it's 5 by 5. It's 25, right? I see a funny face. Do you have a question or just intrigued? Okay. The question is how I got to the 39, and that'll clear up in a second if you let me kind of finish here. Yep. I think we're going to come back to that idea. Okay. That's a great question though, because you're not used to being shown pictures for your algebra, right? So what we're going to do now, and here's the key, we're going to try and write the area of this really big, I almost said triangle, do you hear that? This really big square that we have, we're going to try and write it two ways. Do you agree that this one down here is x plus 5, though, this entire segment, right? And if it's a square, this one way over here better also be x plus 5, and is it? It's x plus 5, right? Okay, so it's also x plus 5. So one way of getting the area of that big thing is I could take x plus 5 times x plus 5, right? Or take x plus 5 and square it. That would be the area of that big one I've got. Everything that you see over there. And another way I could do it is I could add up the pieces, right? This green square here I know has an area of x squared, correct? That's one of the pieces, right? And this one here has an area of 5x. That's one of the pieces. This is one of the pieces of the puzzle as well. And what's the remaining piece of the puzzle? That'll give me the area of the whole thing, the 25, right? Do you agree that those two better be equal because they are both representing the area of that big square? I'll give you a second to absorb that and write stuff down. Okay. And so now let's take a look at what we've got. And so here, I'm going to leave this for right now. Equals, let's combine like terms here, x squared. These can be combined, right? Plus 10x plus 25. Now I'm going to stop you right here. Before we go on, do you agree that this is true? Algebraically, is this true? X plus 5 squared equals that. If you take x plus 5 and FOIL it out, do you actually get x squared plus 10x plus 25? You actually do. Wow, there's some algebra that's foiling. And that's how they came up with that stuff too. They drew pictures for it. They actually constructed it. It's amazing what they could do. I look at it sometimes and I'm like, okay. And they didn't even have X's. They had the big long paragraphs. Just amazing. All right. Now, here's the really neat part. Here's where the 39 comes back in, okay? Do you agree that if I had x squared plus 10x somewhere, that it is equivalent to 39? Down here in my green row, do you see x squared plus 10x written anywhere? Where do you see it? Right here, right? Guess what I get to do if I would so choose? I get to replace that with what it is equal to. What is it equal to? 39. Oh, well, let's do that. X plus 5 squared equals, Now, yeah, we know algebraically this is true, but we know in this case this x squared plus 10x is 39 plus 25, right? So let me know if I get going a little too fast at any time, and if you're listening to the recording and I'm going a little too fast, that's what the pause button is for. X plus 5 squared equals, well, what does it equal now? What, 64? Now this looks really similar to the stuff you were doing yesterday, except you were having to remember all the rules I gave you, right? Or really, it came from this picture, okay? And so now, this is again the case where if you wanted to, you could move that 64 back over, right? Boy, this is something we could graph really easy by that other means we have, right? We can find that vertex point really fast now, okay? And the addition that's really nice with this is now I can go find those x values. I can solve it now, right? Everybody see we're right here, and so let's take the square root of both sides, okay? And here's what the Greeks would have said, right? But we know better, right? Because they didn't consider some things, but let's face it, that's still pretty amazing, right? They didn't consider that negative that we're going to consider, right? From that square root, positive and negative, okay? And then we'll subtract 5 from both sides. So x would equal, so these cancel. You take a positive 8 and subtract 5, and we get 3. That's the answer the Greeks would have gotten, okay? Because they would have just had the positive, right? And then we know that there's another one. Take negative 8 minus 5 is negative 13. And let's face it, in that picture right there, negative 13 doesn't make any sense either, right? In that picture. And so here's the neat part about this. You don't necessarily have to write this down, but we could get an even better sketch than we've been getting before. Now we can move, what, left 5, down 64, right? So we'll just say that point way down there is negative 5, negative 64. And these are the zeros. So x equals 3, so we'll say that's 3. X equals negative 13, we'll say it's over there. So now we got a nice, okay, well, when you do it, hit the points that you make. Yeah, I just make the point bigger. That's how I fix it. See, right there, I make the point. And so there it is. And we knew this parabola opened up from the other stuff that we did. But it's so huge to be able to take something like this, where we started, and get it into this form here, so it can be graphed so much quicker. Okay? And that's where you get conic sections and things like that coming up. And then that's even more impressive, the stuff that they did with that. But do you see the general idea of what completing the square is actually doing? It literally is completing a square. And then I know the other class asked, somebody raised their hand and said, well, how come they only did 2 rectangles? And I said, well, they didn't have to, okay? And so if you wanted to, has everybody got this picture drawn so I can erase it and show you that it could have worked another way? Okay? And so because that's a really good question, don't you think? You know, I was like, wow, that's a great question. And so you could have done it this way, where you actually divide it up into 4 pieces. But then the 10 gets divided up into 4 pieces as well. So each one would be 2.5 by x. And then you complete the square by completing 4 little regions instead of the 1. That's why I like this, the 2 rectangles. You just got to complete that 1 little spot. But do you see how it's still going to add up to 25 if you add up those ones you completed? It's still going to be the same thing. Okay, and that 25 is that constant you would have been making if you did the algebra the way I showed you the other day. Just amazing. Okay, so what I would like you to do right now is I would like you to try this one. Notice I moved the 64 for you, so that's not going to be a problem. Okay, so everything's where it's supposed to be. And I chose 12, so if you want to try the 4 method or the 2 method, it doesn't matter, right? Nice numbers, okay? But I would suggest the 2 method. 2 rectangles, it's easier. Why don't you give this one a shot? Again, it's using a sketch of the Greeks method that they actually constructed with a compass and straight edge. But we're just drawing a little picture, okay? Because we're not as good at them as they were at that. And again, if you are listening to the recording now, would probably be a good time to actually try it and not just wait until the recording comes back on. And just copying it from there. So we'll just pause it and give you some time. All right, let's see how we did. So this again is of that form A that the Greeks had, and so we can use the same picture, and this one's even set up in the right order. And so we start by basically getting x squared in there. So we draw a square and we say it's x by x, and so in other words that would be x squared. And then what we're going to do is we've got 12x, so you can divide it up by 4 rectangles, or you can divide it into 2. I think 2 is just a little bit easier as far as pictures go, and I normally choose these two for whatever reason. As long as they're adjacent, it really doesn't matter. Just don't choose the one on the right and the one on the left. That's not going to work out so well. All right, or the one on the top and bottom. Choose 2 that are at least adjacent. And if I'm dividing it into 2, this will be 6 and 6. Because then the area of this one here is 6 times x, right? And this one's 6 times x, so 6x and 6x. So really it's x squared plus 6x plus 6x so far, which is x squared plus 12x, which is what we have. And so we have to complete our square, which this time is 6 by 6. So the area of that one is 36. In agreement so far? All right. Again, your picture doesn't have to be exactly like that, but should have the same information in it. Okay. And so now what we're going to do is we're going to try and write the area of this bigger one in 2 different ways. So this is x, so up to here is x, and then we got 6 more, right? So x plus 6, and so here it's basically this much is x and then 6 more, so x plus 6. And again, if we are completing the square, we hope to have a square when we're done, and so that actually being x plus 6 squared really, I'm hoping, is not too much of a surprise. So that's one way of writing that area. Another way is to take all the pieces. So here's one of the pieces. Plus, is it okay if I just put these two together right away? Okay, so 6x and then there's your 12x. And then we got this extra here, 36. Okay, and again, algebraically, that's true. Okay. But we have some more information at our disposal at this point. We know that in this particular case, that this value is 64, right? It's right here. It says so. Okay, so I can replace that with 64 and continue on my way like this. And so x plus 6 squared equals 100. Again, this is at the point where you can move that 100 over, set it equal to y, get your vertex if you wanted to. Or we can just kind of keep on moving along and get these answers. So square root, this side houseifies, x plus 6. Again, for the Greeks, it'd just be 10. But for us, plus minus. So we subtract 6. So x equals, well, we take positive 10 minus 6 is 4. And if we do the other one, negative 16. Again, those would be the roots for negative 16. And it looks like our vertex would be at, what, negative 6 and negative 100, right? So it would be down there a ways. But it would come up and hit those, so we would be good. Okay. And so there you go. There are your answers to that. Okay, pretty neat. As I mentioned, why it was paused. This one might take us a while, and you're going to want to keep your work organized because you may be responsible for this at some point. Okay, we're going to solve that one. And we're going to cheat a little bit because we're going to say, you know what? We know there's negatives now. And the funny thing is that other one still works if they did throw a negative in it. They just didn't know that. All right? And so what we're going to do is we're still going to do form A, which it means that that constant is not in the correct location. So I got to move it to the other side, right? So I, in essence, have to solve. So subtract C. I need to solve, and I think we're going to need a full screen here. Ax squared plus bx equals negative C. And this is almost in form A now. One slight change. Because you notice they were very particular in form A, correct? And they're talking of form A. So look at form A here at the beginning. They were very particular about something. Yes? Yeah, there's no coefficient on the quadratic term, right? And they were very specific in that big paragraph they wrote too, that it just said a squared, not 2 times a squared, it was a square. And so this is what we have to take care of now, which means we need to get rid of the a. Now, we wish we could just say a is 1. That would be great. But we're trying to solve every possibility here. And so we're going to divide everything by a. So what we're really dealing with, and I'm going to write this as b over ax because most people prefer seeing it that way. And this is something that I believe most people attribute to a few of the Indian mathematicians. Indian as in actually living in India. Omar Khayyam was one of them, and I always say his name wrong, Karamizi. They figured this out. All right, well, let's draw our picture, because that fits the mold of that other one, because b over a is just a number, negative c over a is just a number, right? Well, here we go. I don't know why I made this one so big. That is x squared, right? That's what we've done first in each of our other cases. Right? And so now in our other cases, we drew these other two pieces, right? And we got our information for that by looking at this term. Wow, that sounds familiar. Looking at that term, and wow, it's amazing. What we're going to do is we split it into two pieces. So we're going to take half of that term. Wow, this sounds really familiar. As in, that's what we did yesterday, right? And so this equals what? B over 2a. So that segment right here is b over 2a. And so is this one over here. I'll write it down here because I got room to. We're going to stop and let you soak that up for a second. So really what you're doing is you're solving a general case. You're making a general solution for this. Okay. Is everybody clear with where we're at so far? Agree that we have followed the rules that were set up by the Greeks. Right? We're following what they said to do so far. He says we're doing it very general. So now we have to actually complete the square, and that is basically b over 2a times b over 2a, right? I would have to take those two, because this is b over 2a, because it is over here, and that's b over 2a, because it is down here. Yeah, b over 2a squared, and I'm going to write it up here because I don't have any room in there. And draw an arrow. Again, we'll give you a second to get that written down and whatever else you want to write next to it. And I'm hoping so far you realize, yeah, this is the same thing we just did, except there's letters there. Right? Ready? So now what we're going to do is we're going to find the area of this bigger square in two different ways. So the first way, well, we know we got x all the way up to here, right? Plus a little bit extra, plus b over 2a. And that will also be the same thing for that side. Right up there, right? X plus b over 2a. And so the area of the big one is x plus b over 2a squared. And I hope you have that stuff written down in red if you wanted to see where b over 2a came from. Everybody got that written down, the red stuff? If you wanted to see that? Yeah, they think it might get in my way in a second. Sorry about that. And if those are listening to the recording, you can always just go back a little ways and see it again. And so now we got to add up the pieces. So let's maybe do that in colors so that it shows up. So we'll do it in green. See, we haven't used that one. X squared is one of the puzzle pieces. And so then I didn't even write it this time, but what's the area of the one I just put a green dot in? It's x times b over 2a, right? So the area of that is b over 2a times x, right? And same thing here, b over 2a and then times x. So we would add b over 2a times x plus another one of those. And then plus, so we got that, we got that, and we got that last one, which you told me already. That little extra piece up there, b over 2a squared, very good. And then we're definitely going to give you a second or two to absorb that a little bit. And this is truly going to test our algebra abilities. But at least two a's on the bottom of it. It's not like there's different stuff on the bottom yet. So that's good. These two terms right here can be combined. They have a common denominator, right? And they have the same variable. And so there's one b there, one b here, and a second b there, right? So it's 2b over 2ax. But what can you do with the 2's? Yeah, you can cancel them, right? So in other words, it's b over a times x. Well, ain't that a coincidence that that's what we had written earlier? No way. All right. So is there anything else algebraically I can do at this point? Well, let's just write this x squared down. Plus, you know what, we might as well just square that darn thing right now. This b over 2a, we might as well square it. So everybody's attention up here. Let's square the numerator. That's b squared. Square the denominator. Be careful. Very good. 4a squared. Excellent. Right? Because you got to square the 2 and square the 8. And I know you may or may not believe this, but algebraically, that's true. So in other words, if you were to sit there and FOIL that out, yeah, that's what you would get. It would work. Right, and I just got rid of those 2 that canceled, right? What is that thing doing? Get off there. Whew. All right. But wait a minute. Wait a minute. What happened in our other problems at this point? Because there's no x on this last term, right? This b squared over 4a squared, that's just a number. There's an x here and there's an x here. It'd be great if we could get rid of those things. Yeah, we substitute stuff in and we look right here. Because you see x squared plus b over ax, right? It's right here too. Right? So I can substitute in negative c over a, right? Again, this is building some appreciation to what some of these people were able to do. I know I'm amazed. And I'm going to give you a second again. Again, no worries. The assignment's quite short today. And so don't worry if time's getting a little short in class or you're listening to the recording and you're thinking, oh my goodness. Everybody ready? Here's where there's going to be some algebra. I'm going to get a common denominator on the right side. 4a squared is going to be my common denominator. So you do agree b squared over 4a squared is good. It's got 4a squared, right? But this negative c over a is lacking the 4 and an extra a, right? So what I'm going to do, if I multiply the bottom by 4a, do you agree I would get 4a squared then? But what's the only number I'm allowed to multiply a single term by and not change the problem? 1. So I must multiply the top by 4a. Okay, do you see 4a squared ending up here? Okay. So in other words, watch how this happens, everybody. It's really a negative 1 that's on the c, right? So negative 1 times 4 is negative 4, right? So it's negative 4ac all over 4a squared, right? Plus b squared over 4a squared. You notice this left side just kind of been like, you know, if you guys on the right side could finish, that'd be great. You know, he's like, it's just been there the whole time. It's like, yeah, if you guys could get done, that'd be awesome. And we are actually very close to being done. And if you have any questions along the way, let me know. And I'm trying to take pauses so you can kind of let it sink in a little bit. So now what I would probably do is, now that we have the common denominator, why don't we put the numerators together? And if you don't mind, I'm going to put the b squared first and then put the minus 4ac. Oh, wait a minute. That sounds vaguely familiar. Yeah, but isn't that supposed to be like over 2a or something? Isn't it? I don't know, something seems strange. But I remember that b squared minus 4ac thing. Right? So now you probably are catching on to where we're going here and what you're deriving. I bet you most of you do know the answer to this because we're trying to get x by itself. Do you agree, though, that this b squared minus 4ac over 4a squared is a number, right? So I'm trying to get x by itself, and x is not by itself, and this square is causing a problem. And so you take the square root, this houseifies, x plus b over 2a, there's your 2a, right? Equals, now watch this move, take the square root of the top, because there's not much I can do there. Now, the other class was wondering, well, why can't you take the square root of that? I'm like, well, it's b squared minus a bunch of stuff. I don't know what that bunch of stuff is and how to cancel it. But on the bottom, you see how I wrote that? I wrote them separately. And you can do that with square roots. Okay, square root of top and bottom separate, just like you can square top and bottom separate. Okay, and let's not forget that that would be plus and minus at this point, right? And so we're going to get a different color. I'll just extend the page again. So what we have now is x plus b over 2a equals, really, I can't do much with that. Unless, because I don't know if it's something I can take the square root of or not. And so that's kind of got to stay. But the bottom, I can take the square root of that. I can take the square root of 4. That is 2. I can take the square root of a squared, which is a. Oh, there's the 2a. All right. And now we're extremely close to, yes, the answer most of you already know. We just have to subtract b over 2a, right? And so in other words, I've got x equals negative b over 2a plus or minus square root of b squared minus 4ac over 2a. And there's that common denominator already that always happens in completing the square, right? And so x equals opposite of b plus or minus the square root of b squared minus 4ac, all divided by 2a. And there is a formula that will solve any quadratic of that form using Greeks and Hindu put together. Miraculous. But you realize somebody at some point had to come up with this, and so it's kind of fun to see what they were able to do with a compass and a straight edge and a little bit of the Hindus gave us the symbols of x squared. He gave us all that stuff. They gave us our numbers, or our numerals, excuse me. Okay. And there it is, quadratic formula. Brought to you via completing the square.
You know how Trevor was here to be young?
I'm pretty sure. But the beautiful part about that one is you don't see it coming until the end. Till right about when I did that is probably about when you saw it coming. I should have left it the other order, and then you might not have seen it. Okay, that's pretty neat. So, any questions? Again, you may or may not have to do something similar to that. At least show me that you know where it's coming from. Right now, I will be honest with you, I'm more concerned if I give you one of this form, can you draw me the pictures and get me the information this way? So, again, same thing, you know, could you do that? Again, you can do it with the 4 flaps if you want, or you can do it with just the 2 rectangles, whatever way works for you.